Hey there, in this video I am going to talk about graph of thoughts. So graph of thought is a kind of a successor to chain of thought. Basically it uses some graph data structures to mimic the chain of thoughts. So like nowadays like more and more research is being done into using graph neural networks and graph data structures into large language models. So basically the main intuition behind this is like human thinking process, it's not a sequential nor it is random. So this can be better mimicked using graphs. So yeah. So this is a kind of a rationale which is used in chain of thought prompting. So like this can be like better mimicked using some graph rather than just a text. So this is a main intuition like because of better encoding of information in form of graphs rather than the raw text. So there was 3 to 6% of improvement on different benchmarks using graph of thoughts. And this is original chain of thought paper by Google. So basically Google used the chain of thought prompting in their PALM model. So in the PLM model was very large language model. So it has like 400 it has 540 billion parameters. So what was so special in chain of thought was like whenever a query was given to a large language model, so the problem was broken down into some n steps. So after a particular query, a particular rationale was generated, and that rationale it was again appended with query, and every time like this was done in autoregressive manner, and like finally our results were better. So this can be like mimicked using another example. So let's suppose there is a one person BINOD who queries a large language model like with some reasoning task like. So first whenever he queries the large language model, so this entire complex reasoning task can be broken down into some small thoughts. So like during the first query, so it will start generating the rationale related to the python, like python is a snake and he has like this kind of nature and he's non-venomous, blah blah, and the so this entire rationale will be again appended to the original query, and the again large language model will be queried. So then again rationale will be generated. So this process goes again and again in an aggressive manner. So until like quite good results are obtained. With the chain of thought prompting, a very complex reasoning answer can be broken down into small rationale, and that rationale are appended to the query each time during one iteration. So this way, like in PALM model, like this step was repeated up to 8 to 9 times in autoregressive fashion, and like because of chain of thoughts process, like the model is able to perform better on the very complex and reasoning tasks. So this way like the large language models are able to perform better on the reasoning tasks. Now let's jump to the original graph of thoughts paper. Graph of thought paper was like successor to earlier multimodal chain of thought paper, which used the multimodal feature like image feature and text feature, and with the 1 billion parameters it was able to beat the GPT 3.5 by 16%. So all that was possible because the data was text like data was multimodal. So similar kind of idea was also used in this graph of thought paper, and it improved by the earlier chain of thought baseline by 3.41 and 5.08% on the particular benchmarks. So like this is like very significant, and like right now nowadays like research research on graph neural networks and graphs in large language model is like a hot topic. Basically like in the future you might even see the large language models are being improved like using this graphs. So all that is possible like because the human thinking process, it's not non-linear and it is not even sequential. This can be better represented using the like graphs. Mm, so explain the graph attention, I am quoting this example like this is a hypothetical example like which can be untrue in the real life. Let's suppose we have a Uber data where we have a pickup and drop off locations of 1,000 rides. So now just we just want to classify whichever location is more prominent in the city, and so that we can schedule the rides according to that. So what we can do is we can just generate the graph out of latitude and longitude, and like we can send this entire graph to just a transformer based graph encoder. So that encoder, like, it will perform the attention mechanism using the adjacency matrix, because like densely connected graphs are like better represented using adjacency matrix, and that after that we are able to classify like some prominent location of the city like CN Tower. So CN Tower will have like a maximum weight. uh, so like let's suppose this will have 0.91 weight, whereas the other locations which are non-prominent which will have like very less weights. This is how like the graph attention works in. This is partial graph attention. Like there are other kind of graph attention which is based on spectral domain, which is like even more integrated than this. So in any graph of thought settings, like there are two steps. The first one is rationale generation and the second one is answer generation. So this can so similar to the chain of thoughts during each forward propagation. So like different modalities of the data, they are just like encoded into the particular vector representation. So we all are familiar with the attention mechanism. So like there is a different attention mechanism in case of graphs and in text, and in case of image too. Like this attention mechanism is more related to text. So this all is done in during first approach. And like for here we have a cross attention, and cross attention is like analogous to normal attention, but it is also sharing the parameters between the different modalities. So after that, a particular sequence of vector is generated, and that sequence is just sent to the fusion layer. Fusion layer is responsible for performing the fusion between the different modalities of data. Like it is also performing single head attention, and it is able to perform the interaction between the graph and image data using the text data. So then like it is sent to the transformer decoder, and transformer decoder just generates some rationale, and that rationale is just appended to the input text, and that entire input text with rationale, it is sent to the graph of thought constructor. So that graph of thought constructor just generates some logical graph out of the entire input text, and this entire steps goes like to 5 or 6 times. It depends upon the requirements of the large language model, and this steps goes again and again. And after like doing this doing this for 8 9 step, this entire like input text is again sent to the large language model, and large language model just predicts the answer. So this is like a high level intuition of graph of thought encoder. This like explains the construction of graph of thoughts. And this is a algorithm. I don't want to dive deep into the algorithm. If you are interested, you can read it by yourself. And these contains the like equations of the textual encoder, which has a multiple heads. And similarly like vision, this is important. This is a feature fusion layer, and feature fusion layer is like it's performing the single head detention, and it's like performing the association or between the image features and graph features. Like it is important in multiple modes of data. Like it is able to uh, generate or it is able to like perform the fusion between the different modalities of data, and finally text is being predicted. Now let's talk about the results section, and it is like quite noticeable from here. Like the graph of thoughts it is beating the previous multimodal chain of thoughts by a significant margin in multiple benchmarking tests. And it is like quite clear from this table that graph of thought has very less parameters. It has less than a billion parameters, and still it is able to beat a GPT-4 chat GPT models which have like hundreds of billions of parameters. And 223 million is similar to BERT large, yeah. So in all the benchmarking tests it's beating the very large models, and it is possible because like we have the additional modalities of data, and like the fusion between the different modalities is like performing the better results than the simple text only models. Sum up from this diagram, it is quite clear that our graph of thought is more generalizable to unseen data than the like multimodal chain of thought, because it has some additional modality like which is graph. So because of the graphs, it is able to generalize better on the unseen data. So this is the power of graphs. So there is one limitation, like graph of thought may result in additional computational cost and slightly slower training time. Yeah, this is because during yes, this is because during each rationally generation step, the again the graph is reconstructed. So that reconstruction has some additional cost. It has like some order of n square complexity because the graph is in form of adjacency matrix. So during each rationally generation step, so there is a complexity associated because we are just reformulating the graph. So that is why it has increased complexity. But like, to sum up, I would like to say that there is a huge potential in LLMs being assisted by knowledge graph and graph data structures. So in the future, you might even see that our large language models like ChatGPT or even the Google ones, they are going to get better and better because of the graphs. So because like a graph encodes the nature of information better than the text. So but there is one problem, like adding a node in a graph takes order of n square time in case of adjacency matrix. So this can be like further approximated, or some approximations can be done on top of it to improve this. And like now what is more, like there is very less research is being done into spectral domain of graphs. So the more research is being now conducted into spectral domain. In the future, our LLMs are going to get better and better. That is all I have to say. Thank you. Thanks for listening. Thanks for giving your time.